Okay, so the topic for this talk should be like learning dynamic sequence patterns with domain-specific priors. So first, I will give some like self-introduction. So as Alex said before, I currently am a postdoc researcher at RPL, working majorly with Professor Hassan. And before that, I worked as a research scientist at a FX Palo Alto laboratory, which is based in California and the United States. And I obtained my PhD from the University of Central Florida, which is also from the United States. And here's some overview of my research. My research interests include temporal data modeling, visual representation learning, machine learning, and computer vision. And some of my presentative previous works, including some works related to temporal order pattern modeling for vision tasks, which include my two papers published on the KDD and the CPR workshop, and another set about of my work is to like the temporal frequency pattern modeling for the various other various sequence data, which also included two published works published on the ICML and the AAAI. And these two set of works should be the main topics of today's presentation. And I also, besides this, I also have some miscellaneous works which relate to the GAN-based training. Okay, so this is outline for today's talk. First, I will give some introduction about the background and the motivation. That what's the kind of a challenge we met to modeling the sequence patterns, and then I will introduce or give more details about my work on like temporal order pattern modeling, and also the temporal frequency pattern modeling. And then based on the previous work, I will brief my research plan with the Digital Future Fellowship. And finally, and at last, I will conclude this presentation. So first is about introduction for the background and motivation. So as you know that AI is quite become more and more like the common or like the populated in the people during the people. Thanks for the advances of deep learning, and in recent years, since the success of AlexNet, the accuracy for the image classification on the large scale data sets has grown fast, and eventually in the 2015 that surpassed the humans performance. So this just showing that deep learning based deep learning based techniques are already dominate the AI's advancement. So, but that means that but this kind of advancements that also have come with a cost. A major problem of the deep learning based techniques is that the deep models usually requires a large amount of accurately labeled data for training. For example, some well-known data sets like the ImageNet, which contains like more than 1 million accurately labeled images, and for the sequence data like the videos, and some public data sets like the YouTube 8M, which contains more about like the 8 million labeled videos. So there's quite a large number of data that need to train successfully train neural networks. So in many of cases, acquire such large amount of accurate labeled data can be very expensive or even possible. For example, when we do some machine translation tasks, which train a model to translate English to the French. So if we just hire some people and give them 5 cents or even 10 cents per word, and if we label the 20 words per sentence and build a data set with 1 million sentence, so it will cost about more than $2 million. And even more for the medical image domain, if we hire some expertise to label the medical images to train a model to detect the nodule and even cancers. So suppose we have expertise can can like label the 10. It will take like 10 to like 30 minutes to label per one image, and the labeling 1 million the medical image may need to take like nearly like 30 years. So this kind of collecting such kind of data is practically infeasible in many cases. So this comes to even harder for the time series data due to various factors. For example, series data may need to consume more computational sources than the image data, and usually like for the time series data that might be more diverse data source, or this means we can have less data source for each domain. And also there are some like privacy or security issues, so on and so forth. So collect a large scale of data sets for the time series could be problematic. So currently, some efforts towards addressing such kind of challenges, including the twofold. The first direction is to like to have like more data available for the training. This doesn't mean this means we need to like hire more people to label data, but trying to like using the unlabeled data more efficiently. For example, the techniques for the semi-supervised learning, self-supervised learning, and even like weekly supervised learning are very active research regions in this direction. But there are second directions which trying to integrating like the domain knowledge into the pure data-driven methods to form some hybrid learning approaches. So this includes like adding additional regularization based on the domain, and even like design special architectural structure for the networks based on some like domain knowledge. So in this seminar, we were focusing on the second direction, which is also my major direction during my PhD works. So first, I want to introduce the temporal order pattern modeling, which we treat like temporal order as a specific like knowledge, which we believe is like widely exists in some like the vision related data. So first, I would like to introduce a method that's trying to mining the order patterns for fMRI based brain disorder diagnosis. So nowadays, the fMRI kind of data is quite important for the medical diagnosis for many like brain disorder related diseases. Usually for fMRI, the medical experts can segment the fMRI based on their knowledge and forming some like functional regions. And based on functional regions, we can detect the activity of the region and extract the activity at multiple region, forming some sequence to activity sequence of that region. But in most cases, there is medical experts need to diagnose some like a brain disorder only based on the observing the human brain's activity and trying to figure out the connection of the regions, and then observing the such kind of a difference and try to do the diagnosis. This is totally like the manual work without involving some automatic diagnosis system. So in this work, what we did is that instead of like ask the medical experts to do the manual diagnosis, we want to figure out some automatic diagnosis system to help the medical experts to make the diagnosis more easy. So this is the basic idea is like this. We use some existing medical-based approaches to extract the activities of each functional regions from the human brain, forming some like sequence model from like a multi-dimensional sequence of the brain activity. Then we project this kind of sequence activities into a set of a latent space, and this will result in like a series of responses towards in the latent space. And for this kind of projection response sequences, we want to find the exact order difference between the healthy people and patients. For example, for healthy people, we want to have a very obvious response of the first one pattern that's always coming to the second, and vice versa for the patients. So that we can just based on such kind of order difference to diagnose the different patients, to decide whether health people and patients are they are. So this comes to our works, which we call them each as a first equal hashing. So this the basic idea for this work is to represent the sequence with the index of first coming latent pattern. So here gives an example. Suppose we project activity sequence into a latent space which includes three patterns. This will result in three different projections. So each projection we will find the peak, or like the peak as the most responsive time for each projection. We recorded this. We record this the time for the peak as the T1, T2, and T3, and then we just order the T1, T2, T3 based on the value of the time. In these cases, we have like the T2 comes first before the T1, and T1 comes before the T3. So in our methods, we usually take the index of first coming response as the index to index the entire sequence. So in these cases, since the T2 always coming before the T1, T3, so we use the 2 as a sequence feature to index the whole sequence. So by projecting a different set of projection, we will resulting in a set of index as a feature repetition, and by binarizing this, we can just have a like 0-1 sequence, which is the output of the FTA hashing. So with such kind of sequence, we can just use it very naive way to classify the patients, people, whether they are healthy people or like patients, by using a very straightforward like classifier like the k-nearest neighboring and so forth. Okay, so this is a basic idea about the first equal hashing, and but during the practice, we also found there needs some regulation to form like clear like response or like the response or peak during the in the projected space. So one regulation should be the orthogonal regulation, which means that we hope each latent pattern should be very identical, not related to each other, since that we can just form some distinct projection, distinct like the peaks at the latent space. So by doing this, we want to minimizing the cosine distance between the latent patterns to force the projection into the later cases. And another important regulation is that we want this kind of responses be salient. So for example, by projecting the sequence, the project sequence can likely to uniformly distributed along the time t from the first frame to the last frame. In these cases, it's very hard to decide whether this pattern is truly appeared or like to appear or have the response in across the time. So we want the project time to be from some very silent or very sharp response from the sequence. So by doing this, we are trying to minimize the variance along the time t to make sure that the projected sequence has a very sharp, very sharp shape and a distinct peak. So by adding the projection, by adding this to regulation for all the FTA training, we tested on public data sets about the ADHD disease diagnosis, and we found some clear order patterns will form between the healthy people and the ADHD patients. Like for first one, suppose we have like the two patterns. So for the healthy people, here the typically developing children means the healthy people, and healthy people. In healthy people's cases, the pattern 1 always come to the pattern 2 before the pattern 2, and for the ADHD patients, the pattern 2 always comes before the pattern 1. So by comparing this kind of different patterns, we are able to automatically automatically diagnose the patients using just very naive classifier like the k-nearest neighbor. Yeah. And also here, here is some more evaluation results on the ADHD data sets we used. We compared with different kind of the temporal distancing alignment technology, which gives us a distance, compare the two distances, give us the best alignment with the sequences. And also we compared with other, baselines, region baselines with our FTA, and you can see that the FTA can just have a very efficient way to detecting to give the good diagnosis accuracy and to the as the output. And okay, so this is basically the first work we did for the temporal order pattern modeling, and encouraged about this kind of results. We further want to extending our order pattern modeling approaches to a more wide range of applications. So next week explored extending the FTA related FTA based method to the action recognition task. So here is some the motivation behind the using FTA to the action recognition. So based on our observation, we find that there are certain order patterns in action videos. The actionlets, which we call the sub action, we call the sub actionlets. Actually, they can form some distinct order to differentiate different kind of actions. For example, the state of a knees. In the standing up action, the state of knees begin with the bending and the going and the changing to the stretching at the end of the video. And for sitting down, the order of the bending and the stretching are reversed. So based on such kind of order of actionlets, we can also help use them to distinguish different kind of actions. So this is basic idea about the order patterns in the action videos. So this comes nature to for us to think about it, like integrating the FTA with the RN. So here I would like to give give some background about the RN. RN is a kind of like the artificial neural networks that recurrently connect itself as at each time step. The RN cell takes the input and update its hidden states and sending and which we are sending to the next time step along with the inputs in the next step and give the results to the give the results to the for the output. And by doing some this recurrent connection, the hidden states will continue to update across the whole entire hidden states. And for the initial or the vanilla version of RN, they have a lot of training problems with them. So very famous problems for the training vanilla is like the gradient vanishing or exploding problems, which means when we're doing the back propagation through the RNN, the gradients will very likely to vanish in just a few steps during the training or explode or become very large that can mass your training. So in order to control or addresses such kind of problems, there are a lot of variants, RN variants proposed. A famous one is a long short-term memory, which using the gates to control the how many input should be remembered, how much the hidden states should be forget. By using gate control, it will propagate the gradients with much further states and partially solving the like gradient vanishing and explosion problems. So inspired by this kind of gated design, so we also can just use the gate mechanism to help us to deciding whether the response is coming and whether we should record the time in order to like have a more complicated order patterns. So this comes to our works for the temporal, which we call the temporal preserving recurrent neural networks. So comparing to the vanilla design of the LSTM, we added the input time t as additional information to the networks, and based on the t, we also like doing some simplify of the LSTM. So the entire cell of the TPRN can be just divided into two different modules. The first one, which is showing in the bottom here, is designed to maintain if a certain stage has appeared or has occurred at the time t. That means when the xt projected, if we just if the response is large enough, we just think this kind of action or action that has happened and then we will update the MT, and based on MT and the XT, we will decide whether this current time t should be remembered or not. So for example, so in these cases, we just help to remember the most important occurrence of the input response, rather than just for the peak. Remember the peak of the reference. This response. This gives us several advantages, so that we no longer just decide the response by using the peak value, and it can be the more resistance to the noise, to the random noises. And also by doing so, we can just change the original FTA from a static fashion into a like recurrent fashion, which can be just running by progressively with like input videos. So we evaluate our proposed TPRN on some action recognition benchmark, including the UCF-101 and the Cherats datasets. We tested with different input spatial features, like the VGG FC6 and the VGG FC7 inputs. As we can see that compared to the vanilla LSTM, we can observe improvements on the accuracy, but not too much. So we further designed experiments to see if the TPRN can really capture this the temporal order patterns. So in this experiments, we select a set of sub-actions and reverse the original video and treat them as a reversed class. And then we train a RN to classify whether the input video is reversed or inversed. So this basically become a binary classification problems. So here we listed 10 we listed 10 classes during our experience, and we can see very interesting results is that for certain classes like the cliff diving, the TPRN can have a very large gap than the improvement than compared to the LSTM. But for some classes like the tennis swinging or rolling, there's not too much difference between the TPRN and the LSTM. So we visualize the videos of the cliff diving and tennis swinging, and we find clear difference here. So for cliff diving videos, we can see that the entire video is changed dramatically, including the background changed dramatically across the frames. But for the tennis swinging, most of the time the background is statics. Only a small region of the image are just changing throughout the time. So this gives us some give us some evidence to showing that TPRN can really help to distinguishing different temporal order for the videos, but it can be also highly impacted by the visual feature. So if the visual feature contains a lot of static background, then it is also still hard to the tracking or the distinguishing or mining the patterns for a very small region. So I think this is the biggest most important discovery for this work. Okay, so basically this is my work for targeting on the temporal order pattern modeling. So another set of my work for is about temporal frequency pattern modeling. This is more efficient to the other kind of sequence data like the signals, audios, or something else. So this also include two different published works, which I will introduce detailed in the following slides. So basically, before we introduce my work, I also want to give some background introduction about why we think about frequency pattern might be useful. Yeah, actually, frequency is based on our previous experience. We know that frequency is very important for analyzing signals. For no matter what the audio signal and the telecommunication and seismology, by such kind of signal data, we usually using many signal transformation, Fourier on the windowed Fourier transformation, vivid transformation, so on and so forth, and to do some the feature engineering works. And this kind of techniques, frequency analysis techniques, are well studied. We know what we will do, and have a good explanation. So that makes our to know, or like to know what to expect, what kind of results we like to given. So for in the deep learning environment, we also trying to like combine the signal related signal analysis techniques with the deep learning, pure data-driven deep learning models. And previously, the typical like signal modeling pipeline with deep learning should like this. We have like the raw data in some like waveform, and first we need to doing some feature engineering, like the extracted like the time frequency features using some like using some signal based transformation, and then generating some like spatial temporal frequency, and then feed the spatial temporal frequency feed some time frequency sequences into deep model RNN deep models. In these cases, we only like the model extracts the temporal frequency patterns through the feature engineering, and for the deep learning part, we only focusing on like the modeling the temporal patterns. So this raises up questions that can we also extend RNN cells to model the time frequency patterns, not just only from the feature engineering, but also inside the deep learning. So this may give more advantages by only like the modeling the time frequencies in the feature engineering. So this is according to this, based on this source, we try to integrating the frequency analysis techniques with RNNs. This is the first work in this direction we did is we call state frequency memory, which can be treated as a combination with the RNN and the short time Fourier transformation. So you can see for the vanilla RNN, we only like doing the forget gate and forgetting and the memory on the time axis. But for the SFM, we're trying to decompose this in inner hidden states into different frequency components. This can be easily done by doing the out product with a set of Fourier bases, which represents a different frequency at each components. And for the forget gate and the input gates can also extend it into the each frequency components to individually modeling the dependencies between the different time step between the different like the frequency. So by doing so, we are not only considering the temporal dependency, but also the frequency dependencies. So forming some inner temporal frequency the features inside the deep learning or RNN cells. So it's not very hard to see that we have by doing so, we can just extend inner states from the vector to a matrix which is not contain not only the different hidden states, but also the different like frequency components. And for this kind of frequency components, there are two options to initialize them. The one thing is trying to design. The one thing is to manually define some like frequency band, such as like pi divided by 4, pi divided by 2, and pi and 2 pi. Such kind of manually defined frequency bands. But also you can also treat the frequency band as learnable parameters and jointly trained with other weights from the RN. So in these cases, the SFM will provide even more flexible the frequency pattern modeling states than the fixed one. So we evaluated our SFM, the SFM on the polyphonic music modeling, and here is the results. We're using the log likelihood to decide the to decide the performance of the each networks. So we use four different like music data sets, and each data sets the music signal is first transcribed into some piano rolls, which corresponding to the keys of the piano. The inputs will have like is like 88-dimensional binary binary vector, where the binary value means whether this key corresponding to the piano should be pressed or not. And by feeding this piano roll like input, we hope that RN can output the next time step the possibility of which key should be pressed in the next time step. Okay, so so you can see that we compared with the LCM and the GRU along with other different kind of related RN structure, and we see that in most cases our methods, the SFM, by modeling the dynamic like time frequency patterns, our method can achieve the best like log likelihood along compared with other deep networks. But also it's also very interesting to see that when for some kind of music data sets, we also observe that vanilla RN combining with some maybe traditional graphical model, which is shown in the middle columns here, given better results than just pure RN related networks. That's also very interesting to see. And besides the accuracy performance, we also investigated how the hidden states activation will look like among the inside of the SFM. So we visualize the two SFM. One is fixed frequency components, and one is the trained frequency components for the SFM. So the horizontal lines represents the number of the hidden states, and the vertical line represents the number of the frequency bands. So here the zero, this is just index, not representing the real frequency band. So we just visualize the hidden states at a different time step, and we can see there are quite significant like differences at a different time step. For both of them, the activation are changing throughout the time, which are like strong at the beginning and then just disappeared as the final. But for the adaptive or like the trained frequency bands, we can see that not only the activation changes, but also the location is changing. That means that means the frequency band are even the changing throughout the time based on like input data. So yeah, this is also very interesting discovery. Okay, so okay, the final one I want to like introduce is about to simplify the SFM with the DWT. So as you can see that when we design the SFM, we expand inner states of the RN from a vector into a matrix. This can definitely make the original original RN cells more complicated. So this in the practice, we also found that by training SFM, the network becomes it will takes longer to converge and maybe more sensitive to the hyperparameter choice. To overcome this shortage, and we trying to replacing the STFT with a more advanced or more with different kinds of transformation, hoping we can just compress the hidden states into a vector, and at the meantime we can just preserve the ability to the temporal frequency modeling. So in this time, we consider to using the RN that combined with the discrete wavelet transformation. The reason we chose the wavelet transform is because that based on the multi-resolution analysis, the wavelet can be forming some space based on like wavelet basis, and wavelet basis also contains some scale factor which allows to automatically to decide the frequency band at the running time. So this results in our next work, which we call the adaptive scale recurrent networks. So in this work, we are no longer project the input with the filter basis, but instead we project the input with a set of wavelet bases. And for the wavelet base, there are different scale associated with the base, and each base we're using Gumbel max to sample from the hidden distribution, and this distribution can be dynamically determined by the time of the different time of input and the previous hidden states. So by doing so, we do not need to preserve each individual frequency band in its hidden state, but rather than we can just using we're using randomly the sampled scale factor to determine whether we should activate each current frequency or not. So I think this is a basic idea about how the adaptive scale recurrent neural networks works. Okay, so we also evaluate our adaptive scale recurrent networks a little bit, and in our evaluation, we found the accuracy performance are quite similar to the SFM, but the adaptive scale RN can result faster convergence speed and easier, and not so sensitive to the hyperparameter tuning, and also for the for standard copy memory problems, we also found that adaptive scale RN can continuously continue to reduce its training losses, while other baselines like LSTM are just stacked into a certain part of the certain position of the losses. So this is basically my works related to the time frequency pattern modeling. So as you can see that by integrating with no matter what the orders and order patterns and the frequency patterns, we can all observe certain improvement for the performance of each of each application, but there seems but the improvement might be limited. That means this can be helpful, but might be more efforts are needed to like further study study how to to further improve the cases. So finally, after introducing my works about the pattern modeling, I also want to mention about my research plan with Digital Future, which were based on my previous works about this the domain specific pattern models, but I want to extend it to the more complicated problems and the more applications. So here is a research topic I'm quite interested to perform at the RPL, and we call this topic as a long-term forecasting, which means we want to generating a long-term future outputs based on the current observation. So suppose we have set of observation, and we have an autoregression model. We feed the observation to the autoregression model, and based on the what output, we can just categorize the problem into different classes. If we expect autoregression model to output some output based on only on the current time step, we just usually treat this kind of problem as recognition. For example, the action recognition, we only care about the output at current time step. And if we just do output the output is just if the output is related to the next time step, we really call this modeling. For example, in the NLP, the language model is always trying to predict the next token. So these two problems are really active, and there already have a lot of works that can achieve significant progress for the achieve significant progress about the RN, but for the forecasting problems, which we care about the output at the t plus k, and k might be very large, for example, by maybe 10 or even 100, and this kind of work is forecasting, and there's not too many works that working on this kind of topic. So there's many the open problems here. That's what I'm interested in here. So here's some challenges we are facing and need to be solved in the near future. So for the forecasting, so most important problem is about high uncertainty during the forecasting. So because that's based on observation, we might have a high confidence to decide what will happen in the next frame. But we will, as the frames go, as the future goes further and further, we will become less and less confident to decide what will happen in the future. So this also means that if we train model, the accuracy will become lower and lower while the future goes far away. So another challenge including the pixel-wise or global level losses that might be very intensive for the temporal saliency. For example, the losses are most of losses just average across each pixels, and if we just back propagate the errors, then each pixel might be equally receive the similar or equally receive the errors, which mean, but in fact as shown in the video action recognition, most of the time that videos have a static background, and only small region of the videos can have that useful information for for the temporal information. So, and this kind of region should be more salient than the static background, but the loss is just treated them equally. So this is not compatible with our understanding. So how to design loss function to improve the temporal saliency should be also problems. And the last one is that evaluating the long-term future prediction is not very easy. As I said, if we just want to try to predict the long future, but basically the output might be diverse, and it's harder to see what may really happens compared to the future. So how to evaluating the trained model is still like the open problems. So based on such kind of challenges, I try to figure out some research direction towards the challenges, which including actually introducing domain-specific regulation to reduce uncertainty. For example, we can based on different for example, we can just have a regulation for like time consistency, as we assume that in the future, if we predict some future and the future output can also like reconstruct the current states. By doing so, we can just rule out a set of possible hidden states that might be resulting in different reconstruction. So, and also it's including some like developing new loss function to better capture the temporal saliency and using motion related inputs. Yeah, but maybe first time is better to like focusing on the introducing domain specific regulation to reduce the uncertainty. So actually, this kind of a long-term forecasting could be very useful in the real-world application. For example, if we're using like the aero remote sensing images, we can just forecast, trying to do forecasting to predict whether the nature disaster will likely to happen, and can just achieve some earlier alarm to minimize the damage. And also for in the medical domains, we can trying to predict that breast cancer from medical images, and along with many like domain spectrum knowledge. For example, the upper outer quadrant of the breast, so on and so forth, to see if a patient is likely to develop some like the breast cancer or not. And then also for the behavior modeling, by modeling the object and their relationships in the scene, we can train a model to understand how the people in the scene, the intention of the people in the scene, and prevent them from doing some harmful behavior when there's a chance that they might be dangerous. Yeah, so that's a brief description of what I will perform in this digital future at RPL. And finally, I want to give some conclusion about my today's presentation. So first is that we know that currently the data is still limited for many domain applications, and collecting the large data set for those domains is not feasible. And we still need to manage works to alleviate the data shortage. And also based on my previous works in this area, so I show that combining deep sequence models with specific domain knowledge like the order patterns and the time frequency patterns would help. But this very depends on what domain it is, and there might could be some like bottlenecks there to yeah, to further improvement. So more efforts is needed in this direction. And also for the more complicated sequence modeling problems, such as long-term forecasting, maybe we also need to more sophisticated method beyond the just combining the spectral domain knowledge with the RN. Yeah, but at least this kind of like this kind of like domain parallel can potentially helpful to help to developing more sophisticated methods. Okay, so I think this is all about my today's presentation.